All right, welcome back to notes for lesson 10.1, day 2. We left off on day 1 having looked at what the difference between convergent and divergent was, and we had looked at investigating different types of sequences and identifying patterns to find additional terms. Now we're going to be looking at using sigma notation to represent and calculate sums of series. This again should be somewhat familiar to you from Algebra 1 and Algebra 2. So example 4, write an explicit formula and a recursive formula for the given sequence. Well, remember, recursive is the pattern, can be found in the pattern from how we get the new term from the previous term. So that one's usually pretty easy to find in the pattern. And then the explicit is where we're looking for an algebra rule. And we have specific ones that generally come up that we'll be looking at in further units. But we're just going to look for patterns and see if we can figure out the rules here for now. So recursive, this one's easy. To get to each next number and the next number in the sequence, you're just subtracting 1. So for our recursive formula, a sub n is a sub n minus 1. That's the subscript, saying that it's the previous term, minus 1. But we do have to say what a sub 1 is. In this case, a sub 1 is 15. So whenever you give a recursive formula or a recursive rule, you have to say what the first term is. Or if you're going to base it on 2 previous terms, and you need to give the first 2 terms, or 3 previous terms, then you need to give the first 3 previous terms. So there's one of our answers right there. That is the rule for recursive. And for the explicit, well, keeps going down by 1. If you remember back to Algebra 1 and even Algebra 2, if there's a constant difference between these, then it's a linear equation, and the slope will normally be the constant difference. So in this case, it's going down by 1. It's going down by 1. So we have a slope of negative 1. So for our explicit rule, we're going to have a sub n equals negative 1 times n, because we saw that constant slope of negative 1. And now we're going to see what we'd have to add to this to make it work. And then we'll also double check that it works for all of them. So negative 1 times 15 is negative 15. Actually, negative 1 times 1 is negative 1. So to get a positive 15 here, we'd have to add 16. So I'm going to check this right now. This is the first term. So for a sub 1, I'd have negative 1 by 1 plus 16, which would give me 15. For a sub 2, I'd have negative 1 times term 2 plus 16. So that'd be negative 2 and 16, which would give me 14. And I just need to double check. You can check either in the calculator or by continuing this to make sure that your rule that we've just come up with will continue to work for this pattern. Take a second to look at the next pattern. It's a little trickier, but you might see what's going on, particularly as you find the recursive rule. So for our recursive rule, we have from get to here to here. Some people thought, oh, subtract 30, but that doesn't work to get you to 40, so that rules out. Other people thought, well, just times 2. Okay, except it's negative, so you'd actually have to times by negative 2. But then wait a second, if you keep doing that, that pattern does work. So our recursive rule is a sub n equals negative 2 times a sub n minus 1, where the first term is 10. There's our recursive rule. So it says, take the first term, times it by negative 2. Take that term, times it by negative 2. You want the third term? Go to the second term, times it by negative 2. Our explicit rule, not as easy to come by as when it's a linear equation, but still possible. We know that they keep multiplying by negative 2. So it's one thing when they keep adding something, that's like our slope. When they keep multiplying by, thinking of families of functions, where you keep multiplying by a number. Now I know it's negative, so we'll deal with the negative part in a second, but keep multiplying by 2, it's like 2 times 2, or like you're multiplying by 2, and then you're multiplying by 2 again, and then you're multiplying by 2 again. That's 2 to the third, that's 2 to, so we're dealing with an exponential function if you hadn't already figured that out. So we're going to use an exponential function, but it's got to include a negative, otherwise the sign won't change back and forth. So we're going to look and see if this will work. We're going to do, we have to have an initial amount when we have our exponential equation, but we're going to be multiplying by -2. Well, our initial amount is 10, so I'm going to put that right there. 10 times -2. Okay? And so if it's to the first, great, it gives us -20. If it's to the second, it gives us 40. Third, but we have a problem because 10 times -2 to the first gives us -20. But that, if I make this n, we have a problem because this would be the first position. This 1 represents position 1. Well, that's a problem because position 1 is actually 10, not -20. Now, I just want to make sure the pattern continues, and then we'll deal with that in a second. But we've got 10 times -2 squared. Well, that is the next number on the list. If you put it in, it is going to be positive 40, so that's good. And 10 times -2 to the third, that does end up to be -80. The problem is these are each off by a position. Position 1 is actually supposed to be 10. Position 2 should be -20. Position 3 should be 40. So what we're going to do is we're going to make our exponent n minus 1 since they're off by 1 position. Because now if I plug in 1, 1 minus 1 is 0. And 10 to the 0 power is 10. And here, the second position, we're doing the first term, second term, third term. So in the second position, 2 minus 1 is the first power, which would give us the -20. And then 3 minus 1 is squared, which is going to give us the 4 times 10 is going to give us the 40. So now they're working out to be the numbers we want and in the correct position. So this is the explicit rule for that one. We're talking about a series. A series is the sum of all terms in the sequence. And so we have like a sequence like 1, 2, 3, 5. The related series, so if that sequence only has those 4 numbers, the related series would be 1 plus 2 plus 3 plus 5. Now, we can have finite series like the one we just did. Okay, it's associated with a finite sequence. Basically take that finite sequence and just add all the terms. We also have infinite series, and for our infinite series, we would take the sum of an infinite sequence. So this is sum of a finite sequence, which we saw an example right there. Infinite series is the sum of an infinite sequence, such as 1, 2, 3, 4, ... So then the related series would be 1 plus 2 plus 3 plus 4 plus ... And would keep adding the next number. We also can do the nth partial sum, which means if we have a series, typically an infinite series, but if we have a series, we can do partial sum, which is from the first to whatever term. Maybe it's from the first to the third term. Maybe it's from the first to the 100th term, even though this one's infinite and keeps going. So we can do the nth partial sum, and that is actually denoted with a capital S and a subscript n. And so what that means is, let me give you an example. If I had S sub 3 from these numbers up here, then that would give me 1 plus 2 plus 3, and I would get 6. But if I had S sub 4, oh, by the way, that was the sequence, or the series 1 plus 2 plus 3 plus 5 plus ... And since it's S sub 3, we just did the first 3 terms. So there's an an example to show us the nth partial sum, what that means. So an example of this, in example 5, finding the nth partial sum, the sixth partial sum, so we need the position n to be 6. So what I need then is, what I'm basically going to say is s sub 6 equals, but I got to find all of them, because here's the thing, this is a recursive rule. A sub 1 is 8, and so that's our first term, so that's position 1. We need to get positions 2, 3, 4, 5, and 6 before we can actually add these. So what this says is to do half of the previous term. So I'm going to do half of 8, half of 4, half of 2, half of 1, half of 1/2. And I'm going to add those up. That's going to give me 10, 11.75. Oh, wait a second. I feel like I did something wrong. Is that all 6 terms? This is 8 plus 4. I added wrong. Sorry. This is 12, 13, 14, 15.75. 15.75 would be the partial sum. This recursive pattern, because they don't tell us when to stop for n, is an infinite one. It'll just keep going on. But we only had to do the first 6. So give that a try for letter B. This one, they actually give you the explicit formula. You can take a moment to pause the video and plug the values in for n. So for s sub 7, you actually are finding the sum of 0.3 if you did this for the first. The second one is 0.03, 0.003, 0.0003, 30 thousandths. And then we have another 1, 2, 3, 4. We have to do this 3 more times. So you keep putting that in the calculator. These are the first 2, 3. Then I'm going to have 4 zeros after the decimal. Then I'm going to have 5 zeros. 1, 2, 3, 4, 5, 6. Last one, here's the 7th one, 0.6 zeros in front of the 3. We put this in your calculator, and honestly some of you don't need to, because if you just know place value, you know that this equals 0.3333333. I missed one. 3. So there we go. So there's the sum, which is could be approximated by 1/3, but it's not equal to 1/3. Now, if we did this infinitely, then we just keep adding 3's here. So if this weren't a partial sum, but they were asking for the actual sum of the whole series, an infinite series that's expressed by this rule, then it would be exactly 1/3. All right, let's take a look next at sigma notation and how we can write things using sigma notation. Okay, so here we go. We've got sigma notation. And sigma notation, we have this is sigma, the Greek letter. And we have for any sequence that's going to be added or that's going to become a series, we have a highest value up here, and we have an initial value down here. So you can actually take sigma, you've probably seen it in Microsoft Excel, for those of you who have used Microsoft Excel. If I have a bunch of numbers, let's see if this is actually going to open. Yeah, it's not opening, that's fine. Maybe it is, here we go. If I have a bunch of numbers, I can actually put them together real quick. So like 2, 3, 4, 5. And if I just hit this auto sum key, it'll add all those numbers together. Or I could even click on that and click which numbers I want to add together, and it'll do the sum. So that's sigma notation is familiar to some of you who have worked with Microsoft Excel, or if not, now hopefully you know a new trick when you do go to use it. Anyhow, so we're doing the sum from, in this case, the first term So I'm going to put equals n equals I for initial instead of 1. I know the book puts 1, but sometimes we're actually going to do the sum from like the 3rd term to the 9th term. So you'd see a 3 down here and a 9 up here, which would tell me whatever the sequence or whatever the related sequence or the actual series is, I'm going to do it from this position to this position. N equals this to n equals this maximum value. Minimum value I put in, maximum value I put in for the position. And there should be an explicit rule. A sub n needs to be written as an explicit rule. Well, we prefer an explicit rule. Will tell us how to generate the terms. So it's going to give us a rule that we can plug in this position and then all the ones after it till we get to our max position. And then we'd add them up to take the sum. This is called the upper bound. K is called the upper bound for the position that's being put in. And I, which they have as 1, is the lower bound that you're going to put into whatever function this is. So let's look at an example. We're supposed to find the sums using sigma notation. So here's the notation. We're supposed to find the sum from 1 to 5. So that means this could be an infinite series. I could just keep plugging in values. But the first one they want me to use is 1. So I'm going to find the value of of position 1, of position 2, of position 3, 4, and 5, and I'm going to add all of those together. Okay, so the top will be a sub n. These will be my numbers, and it's not going to be a fraction. It's just I'm kind of separating this problem by writing what the positions are, finding each output for those positions, and adding them together. So in my calculator, I'm going to do n squared minus 1. Better do that in parentheses because it's all over 2. So then I input 1, 2, 3, 4, and 5. And I get these values. I get 0, 1.5, 4, 7.5, and 12. And I'm going to add those together. 0 plus 1.5 plus 4 plus 7.5 plus 12. So this sum right here is equal to 25. And here's my work for it. I found each of the values, the outputs for each position, and added them together. For letter B, it's also that simple. I'm supposed to start from the 7th. That's a 7 position. So 7, 8, 9, 10, 11, 12, 13. This is n equals 7. This is n equals 13. I'm going to have to find those using the algebra rule, the explicit rule, n cubed minus n squared. So n to the 3rd, not 2. X to the 3rd minus x squared. And so I put that in my calculator, but this time I need to start at the 7th term, not the 1st. So 7, 8, 9, 10, 11, 12, 13. This gives me, lots of big numbers. So 294 plus 448 plus 648 plus 900 plus 1210 plus 1584 plus 2028, 7, 8, 9, 10, 11, 12, 13. Got them all. So now I actually take the time to add those. And I get that sum is 7,112. Take a moment to try letters C and D, and we will go over those in class tomorrow and go over a little bit more if there's any confusion about sigma notation and how it works. You'll have practice in class, and then we'll move on to the next lesson. Have a great day.